Okay, once again this is Dr. Bob, and today we're playing with the Space Telescope all over again. Well, not all over again. This has been going on for probably about a year. So, what I've done just recently, I was looking at the voltage multiplier. This is just a diodes. What you see here is diodes and capacitors, and what happens is I've got the one end of a transformer right there. Here is the left end or right end of a transformer, and what this transformer is it's a 10-to-1 basically. It starts out, and what it does is just transformer pushes juice in this capacitor and puts a charge out here, and the charge gets pushed through these diodes or pulled through this diode, and then it gets pushed up the line, goes onto this capacitor, and then transferred through. This one, as the charge goes up and down, it charges these capacitors, and the diodes collect the juice and they push it up through the next capacitor, and so on and so forth. So I had it out to here, and at the highest transformer duty cycle I could get, which was about 50%, was pushing this around 700 volts. And I thought, man, I wonder if I can boost this up a little bit. And I thought, let's just for the heck of it, let's throw in a couple of inductors. And what inductors are current devices. And so right here I threw in an inductor and another inductor, and of course I went through the simulations, and the ideal perfect inductor was around 68 millihenries. And so one here, and two more here, and then two more here. And every two inductors, when I put it into the circuit, this thing really kind of boosted up. I mean, I was sitting on 700 volts out here somewhere, and yesterday I was playing with this guy after this guy around this one or this one, and it was up around 4,000 volts, and I said, this is nuts. Now I want this to go to at least 15,000 volts. Like I said, I've been playing with it, but it also needs to be infinitely variable, so depending on what the pulse width that I put on this thing over here, which is really, and these are the more inductors, right? L6, L7, L8, L9, L9 over here, and then of course 11, 12, 13, 14, 15. I don't know what these are going to do, but I mean I've got 4,000 volts over here. I'm not sure what I'm going to get at the end of this monster. We're looking for 20,000 volts if we can get it. Here's the other end of that inductor. And the problems in this configuration is that you only get about maximum 50% duty cycle. So I redesigned this circuit over here. This is the circuit controls the input. This is the gate to this device that controls the duty cycle of this device over here, and this device over here goes to the T1 winding of that transformer that goes over to the other side of this transformer here. So this transformer over here feeds, it provides power. Now what we've taken is struggle transformers. My original transformer of these guys, this is a one-to-one. This is a one-to-one big transformer. It's a pulse transformer I got off. And these are about maybe $1.50 a piece. And this one, as you may or may not recall from my last video, burned up to a cinder. I bought two of these, and the other one just burned it up. I'm trying to figure out what I do. I might have thrown it away, but it just couldn't handle the heat. The power's hooked up. I got a new transformer here, and this is just a regular 100 to 9 volt, 100 volt, and it converts it to 9 volt. And what I've got is reversed, so that I got the 100 volt over here, and the 9 volt over here, and the 100 over here. So this becomes a 10-to-1, or 1 to 10. So it takes 100 volts and it converts it into 1,000 volts. So what we have coming over here, every time I hit this with the pulse width modulator, this sends out 1,000 volts. Now all this sends out 1,000 volts. So these capacitors are rated for 1,000 volts. These diodes are rated for 1,000 volts. All these is 1 in 4007 diodes rated for 1,000 volts. So this should be able to handle it. Now the thing about a voltage multiplier is it might have 1,000 volts here, and then I might get a 900 volt over here added to it, so you get 1900, and then over here you get in the next stage you get maybe 2700, and instead of, or 2600 because it goes up 800. So each stage you go up, it loses a little bit of it in a transfer. Now it's not 100 volts each time, but it drops down by a certain percentage, and by the time you get down to, you know, all these, and then you get to all these, you're down to the last one is only adding 10 or 15 volts per stage. So that's when I thought about getting the idea to put in these inductors and see if I could put a booster on it. Oh, like son of a gun, this got a booster, and it really kicked it up. So what we're going to do is I've added another stage. I've got L6 and L7 in here. Those are 2 more inductors, so I've got 4 inductors total. You can see here's the circuit right here. It's inactive right now. So there, that should be on, and we should be getting 100 volts. Right over here. So this should be 100 volts. So I'm going to put this on there. That says 99.8, so it's drifted down a little bit, and I don't know if I want to fool with, I don't know if you can see that. Let's see, that's 99.8. We can see this is 99.8 volts, and I'm going to reconnect this lead over to this. Now what this is a 1 gigohm resistor. I never heard of one or seen one before, and I thought, well, how am I going to measure all these high voltages? And I started reading up on it, and this resistor is 1 billion ohms. I've never seen one before, and now I have one. They were about 50 cents a piece, so I bought 8 of them, and it's even reading a volt right now. But this is basically a divide by 100. It's a voltage divider, not a voltage multiplier. So it takes whatever voltage here. This has a 10 megaohm input resistance, or input impedance. So 10 megaohms divided by 1 gigaohm is a difference of 100. So this is a divider, voltage divider. So whatever comes over here, for example, if I see a 60 volts over here, multiply that by 100, and it'll be 6,000 volts. So, without too much, we hear the 4 inductors, 1, 2, 3, 4. I'm going to be careful not to touch this, because right now this is a live circuit, and as soon as I turn this on, I'm going to start getting some pulse width modulation over here, which I'm going to control with this little knob right here. Then we're going to start seeing voltage coming across here, and it's going to be high voltage, which means not on the top of this, because if this sees 60, that's what's going to be there, and I can get shocked by the 60, but what's down below that resistor is going to be 6,000. So, like I said, the last time with the other setup, I was able to get this up to 700 volts. And we're going to watch this as I turn this. I'm going to turn this, and I'm going to rotate this until I start getting a little bit of a glitch over here, a little bit of a bump. Okay, now there's the first little bump that just popped up. Now that's intermittent bump. It's not doing it every single time, but even at that I'm getting a 17 over here, about 17 volts, and that translates to basically 1700 volts, 1700. Now that's already 1,000 volts more than the first. Well, I mean, this just had these 4 inductors. That's all I did. Well, that's not all I did. I added this 10-to-1 transformer, which made a really big difference. And I probably should have tested the transformer before I tested. And I think I did test the transformer before, and it wasn't really all that much higher. So, alright, so we've got it on maybe 2 or 3%. Well, let's take this up a notch and see what happens. So I can tell you right now, this device right here is already getting hot. I'm also watching this current here, and it's down near 0, and I'm getting 1700 volts out of this thing. And I'm very happy about that. I mean, this is what we were looking at to see how much current this thing was drawing. Okay, so I'm going to take this up a little bit higher. We're going to look at that. Now we're getting, I don't know what this is, but as you can see, the current has jumped up to maybe 1/4 of an amp. And the voltage has jumped up to 41. That's 4,100 volts already. So, wow, that's quite a bit, 4,100. I'll take it up a little bit higher because what I'm looking at, and I'm watching this, but I'm also watching this. I'm watching this more than I am anything else. As I increase the duty cycle, as you can see, that duty cycle is getting a little bit bigger. The current's starting to go up. It's up at 1 amp. And now it's up at 1.5 amps. What do we've got over here? We've got 7,000 volts over here. It's 70. That's 7,000 volts on the end of this thing. Wow. Now, the thing is, I think this is the most duty cycle that I'm going to get out of this, because as I push this up higher, this is 1.5 amps, and it really shouldn't be over 1 amp. And right now, that means this device here is getting hot. I can feel it. Now this device is not getting hot because it's 1.5 amps. Look at that jumping around because I'm pushing on this. Now this is, the current is not being taken up by the circuit itself. It's being taken up by this guy right here. And that's because this pulse width modulator is not tuned. It's not balanced. I put a 1.5 microfarad capacitor right here to try and balance that circuit, but I think I might have to, and I thought that would announce. Okay, so what's happened here is we've you can see it's gone up to 4 amps, and that's just too much. It's just popped up there. I've turned it back down, and that was only, at this point, when it goes up to 4 amps, this thing is delivering everything it possibly can deliver, and even this transformer over here is getting warm. And what happens is that this transformer goes into saturation. That is, it can't really deliver any more pulse width modulation. It means it can't do anything with all the current that's going into it on this one wing here. So all the current is going here, and if we look back at the design, what it's saying is that as long as it's keeping under a 50% duty cycle, and we're still at 6,100 volts, by the way. This thing is still, that's this transformer right here. This is the pulse width modulation circuit over on here. And this transformer is trying to take up all the current, all the energy is being into it, but it doesn't have anywhere to go. For 50% of the duty cycle, it goes down, it gets shorted down through, basically, this MOSFET, which is this guy right here. Now this is just the cooling pin. What you're seeing here is the cooling pin. The actual MOSFET is that guy right down inside there, that little black thing. And that thing is giving up all of its energy. It's taking up half the energy, but if it can't take up at least half the energy in this thing, actually all the energy, then this thing will eventually just go straight into saturation, and it'll say, I can't take any more current, I can't do anything with all the current. And that depends on the duty cycle over there. Now, theoretical maximum is 50%, which is what I redesigned these two circuits over here to go a maximum of 50% duty cycle at 10 volts. But this can go more than 10 volts. This can go up to 12 volts. And that's something I have to fix as well. But, as you saw, we're sitting at around 6,100 volts, and I only need 15,000. And I've got 8 more of these guys to go in. So I think I'm going to hit 10,000 easily, and maybe even 15,000 without having to do the full duty cycle. So let's take a look and see. I'm watching both of these. Let's see, watch, if I take this up, it's up at 2 amps. And at 2 amps, it's at 7,000 volts. So, I don't really need to go any higher than this duty cycle right here, which appears to be about I'd have to measure this. And it's supposed to be 50 kilohertz, not 42 kilohertz, which means that some of these are not appearing where they're supposed to be. Which makes me wonder why it's glitching like this. So I suspect there's something else going on here. My trigger mechanism for this device is going to be, and let's take this, my trigger mechanism should be this little thing right here, and as long as this is doing what it's supposed to be doing, we have what we're supposed to have. So this guy, I'm going to take a look at this one a little bit more. Let's take this down to 5 volts. Alright, so that's, we trigger on channel 2 instead of channel 1. We should be triggering on this right now. Everything we see here should be coming up over there. Now we're up to 4 volts. That means this thing is popped up. Well, now it's gone to 0, which means something stopped working. Something overloaded and said, I'm not going to do this anymore. And I don't know what it is. It might have been the aluminum foil I have wrapped around that fuse over there. It just died and gave up. And I'll bet you I've lost, let me check something. This says 3.9 volts, so it really has dropped. It's carrying a charge. It's carrying a 33 volt charge. Let me see if we still have the 17 volts over here. Okay, so here's what died, is that we only have 0.02 volts. So this thing has a residual charge on it, and apparently something over here has decided to stop working, which happens all the time, and I don't know what the heck it is. I play with it, I go in there, I look at it, I try to troubleshoot it, and then boom, it starts working again. I'm going, what the heck is going on around here? My suspicions are this little fuse, which died a long time ago, because it's only 2 amp fuse. I wrapped aluminum foil around it, and I wonder, because I hear it crackle every once in a while. So anyway, yeah, I can start fires in my house with this stupid thing. Anyway, that's doing what it's supposed to do, but when I hook that other stuff up, it starts to jump around, which is kind of odd, because this circuit has nothing to do with that other circuit. So, actually, it does borrow the 12 volts to do that pulse width modulation over here. So those 2 circuits are associated. So the last little thing on this is the pulse width modulation. For some strange reason, when the 100 volts is not attached or working, this works wonderfully. So you can see that actually goes out to about full 50%, but when I push it over 10 volts, it goes too high. And of course, we never got anywhere near that. We got it down to about right there, which looks to be about 35–40%. So apparently that's how far we're going to be able to get it. This little part here is just the trigger that sets off this bit of stuff that happens. I don't know if I want to try and explain how this works or not, but it really is pretty interesting the way that works. I mean, you can look at, well, I'm not going to try and explain all that. It is based on the capacitor and resistor values of these guys down here. Don't worry, nothing's connected. I haven't reconnected that at all. So that's the latest on the space telescope, and of course, when we need this space telescope, once we get this the power supply, the high voltage power supply fully designed, what I'll do is I'll have lay it down, and I'll send that design off to. I'll have to do layout and have printed circuit boards built up. So we need 8 of these for every telescope. So 8 of whatever you see right here. And actually 2 of those, because this is just the positive end of the power supply. There's actually a positive and a negative side of this power supply. So it'll be plus 20,000 or plus 10,000 volts or whatever this comes out to, because I don't know. I do the simulations, I do the calculations, I do the approximations, but you don't know what it's going to be until you build the circuit and see what's going to happen. So, which is why we test things. for us. And at this point, we saw 7,000 volts after on the very low end of this circuit, which is, you know, that big. So I'm saying 7,000 volts over here, might be up there. So whatever I can get up there. But this will be, as I said before, an infinitely variable, and it's not really an infinitely variable. I should be able to vary by about 10 volts. As you can see, that's probably not perfect, and I still got to figure out why there's this glitch in here that doesn't seem to, you know, it just pops up occasionally. So that's something that needs to be worked out. But in the meantime, we know that NASA needs a space telescope. This is it. We need eyes in the skies because we don't know what's out there that's coming to get us. Whatever killed off the dinosaurs could come around and kill off us. This is easily. So we need eyes in the skies, and we need lots of them because there's a lot of stuff out there. We don't know what it is. There's stuff we don't know what it is that could destroy us, whether it would destroy us. There's a thing out there called the Great Attractor that's eating entire galaxies. And guess what? This one's next. And as old as this galaxy is, you know, it's unbelievably scary because we can't get stuff out there where we can see because we need lightweight telescopes. I got to get the PC boards made. That's probably going to cost me about $180. So if you want to make donations, just send me a check and help me out with this stuff. This is Dr. Bob, saving your ass and mine from space alien monsters and asteroids. We'll see you next time. Thanks for watching my program. If you like my videos, be sure and subscribe to my YouTube channel. And for an organized listing of my YouTube videos, go to my website, www.wherearemyplacebos.com, and click on videos. Have a great day.